Hello, my name is Ariana Verboski, and today I'm going to be presenting to you this research on Rosette nanostructures and the analysis of micromixing capabilities. This research was done in collaboration with Dr. Wayne Strasser, Dr. Hector Medina, and Robert Kaczynski. So first, to go over the objectives of this research. The objectives of this research were first to develop and create a functional CFD model of fluid interactions around a single rosette, then to observe the Rosette nanostructure's effectiveness in the mechanical micromixing of two fluids, namely in this research air and moisture, and to contribute to a larger effort to investigate the applications and capabilities of the Rosette nanostructures. Now to provide some background information on the rosettes themselves. The rosettes are a novel rose-like formation with nano-thick petals that were observed and discovered on acid-etched titanium during the research of Dr. Hector Medina to investigate the modification of structures on the surface of titanium for applications in implantology research. This project is part of a larger effort to analyze fluid interactions around these structures to investigate their effectiveness in assisting with mechanical micromixing of multiple fluids and chemical reactive flows passing by in order to investigate the claim that these Rosette nanostructures could be used in micromixing applications. The values of the flow parameters used for this CFD model and analysis are detailed below. In our Reynolds number, it was set to be 0.1, and we used for our density a density of air, which was about 1.2 kilograms per meters cubed. Our length scale was set to be the length of the Rosette scale, which was about 30 microns. Then our dynamic viscosity was set to be 1.7 e to the negative fifth Pascal seconds. Our velocity was then calculated from our Reynolds number to be 0.0472 meters per second on average. Here you see a schematic of our model looking into the inlet face of the flow. As you can see here, we have two stratified layers of fluid, the bottom layer being air and the top layer being moisture, or water vapor, as used from the Fluent database. In the bottom layer, in the air, it is set to be about 1 rosette height tall, and the moisture above it is also set to be about 1 rosette height tall, making the entire channel about 2 rosette heights tall. On the top and the bottom, we have no-slip walls that, when looking into the inlet face, are 5 rosettes wide. As you can see in the bottom right of this schematic, we have the half rosette modeled and included in the channel. Half rosette was modeled for this analysis due to the fact that the rosette geometry is symmetrical, and this was done to ease calculations. Now we look at a schematic of the model looking into the right side of the channel perpendicular to the flow. The channel as a whole is a rectangular prism, and thus we have a rectangular cross-section again. We have on our left-hand side the inlet, and then on the right-hand side is the outlet. The entire channel is 2 rosette heights tall, as detailed before. And as you can see, the rosette itself is set to be 3 rosette widths downstream from the inlet and 5 rosette widths upstream from the outlet. As you can see here, you see our no-slip walls and the direction of our primary fluid flow. Now to look at the geometry that was used in the model. Here is the geometry that was used for the rosette half. The geometry was modeled in SOLIDWORKS 2020, and the rosette height was set to be about 8.08 microns with a diameter of about 28.61 microns. For the meshing scheme, we used a blocking method, and so we had the cylindrical block that encompassed the rosette itself as well as the fluid volume immediately surrounding the rosette. The cylinder itself was about 55 microns in diameter and about 16.151 microns tall, which is 2 rosette heights. Then, outside of the cylindrical block, we had a rectangular block. The overall dimensions of this rectangular block make up the overall dimensions of a rectangular channel, and were said to be about 143 microns wide by 257.5 microns long by a height of 16.151 microns, or the height of 2 rosettes. The center of the rosette was set to be 100 microns from the inlet face. Here is pictured a representation of all of the pieces of the blocking and the geometry put together in a single assembly. Here is pictured a mesh that was generated for a rectangular baseline case where the rectangular channel was created to be the same dimensions as that of the channel with the rosette introduced. However, this case was a preliminary case and did not include the cylindrical or the rosette geometries, just the rectangle, and was used for comparison as well as initially generating the meshing scheme. These were the most recent meshes that have been run for 6 cases that we are going to detail in the following slides. This mesh in particular is related to cases 1, 2, 4, and 5, and was a polyhex core mesh. We have 2 versions of this mesh. The first version is pictured here and was used in case 1 as well as case 4, where case 1 had no rosette being present and case 4 acted as if the rosette was present. Then in version 2, it was very similar to the polymesh version 1, except that in the inflation layers coming off of the rosette, the first cell height was set to be 2/3 of that of version 1, and also version 2 had half the number of inflation layers as in version 1. Case 2 and case 5 make use of the version 2 mesh, where case 2 has no rosette and case 5 has the rosette introduced. Then, for cases 3 and 6, we used a rectangular and tap mesh, where the rectangular block was meshed using the same meshing scheme seen in the preliminary rectangular baseline mesh, where it was all quad mesh and all rectangular. Then, the cylindrical and rosette geometries were meshed using tap meshes. The total cell count for this mesh came out to be about 9.6 million cells. And in case 3, we had no rosette, and in case 6, the rosette was present. Then we had our model solution set up. In Fluent, we used the species transport model. We had 2 species, we had air and moisture, and as mentioned previously, our moisture was set to be water vapor from the Fluent database. Our velocity inlet boundary conditions were set to be a Couette flow profile using a UDF, and our average velocity was set to be 0.0472 meters per second. We used an SST turbulence model with 0 turbulence inflow, and this was created to be a not strictly transitional model in order to eliminate any of the effects of induced turbulence from the flow just traveling down the channel in order to be able to isolate and determine what turbulence was actually being created by the rosette itself. Then in our solution method, for momentum and species, we used the quick solution method setting, and all other settings in the model were the default settings. Now looking at our results. So here you see pictured the velocity profiles at the outlet for 3 meshes that were run initially. We had a no rosette with a quad mesh, no rosettes with tets, and then rosettes with tets in our mesh. And as you can see here, the presence of the rosette did not appear to change the velocity profile at all. With no change in the velocity profile with the presence of the rosette, and it staying very laminar flow, this means that the rosette may not be inducing any mixing or turbulence at all. Then, in looking at our pressure drops from the last 6 cases that have been run, we find that our pressure drop was about 9 pascals for all 6 cases, with the difference between the non-rosette cases and the rosette cases only being about 0.1 pascal, which is not a significant pressure drop at all and indicates that the rosettes are not really disrupting the flow at all. Now we have a normalized moisture concentration profile at the outlet for all 6 of our cases. And as you can see, we have our inlet case as well. And the inlet has a step profile while the others all deviate from that. And this deviation from that initial step profile indicates that there is diffusion happening in the mesh regardless of whether the rosette is there or not, which indicates that there is some diffusion and some mixing happening even just in the mesh itself. And we found that our rectangular tap mesh had the least amount of diffusion, but due to the fact of the presence of tets and non-conformal faces, this mesh is still not ideal. And the difference between case 3 and case 6 as you can see with rosette or non-rosette, even with our best mesh so far, the results indicate that the presence of the rosette does not make a difference as much as the difference in the meshing scheme does. And you can see a similar story here with our species gradient profiles. And as you can see, there is greater diffusion happening with all of our cases at the outlet than at the inlet, which indicates again that there's diffusion happening throughout our meshes. Here we also have our static pressure contours to help visualize the flow and what is happening around the rosette. As you can see, the flow is barely disturbed downstream from the rosette, and really most of the disturbance is only happening in between the petals of the rosette. And as you can see by the vorticity contours, we also only have vorticity really happening on the edges of the rosette itself. So in conclusion, the rosettes do not appear to be altering the velocity profile at all, indicating no induced turbulence from the presence of the rosette. And while our SST turbulence model was not set up as a strictly transitional model, and we might need to add an LES model instead, this still would not solve the problem of determining whether or not any induced turbulence is happening due to the rosette. Then, in our meshing scheme, we found that the meshing scheme makes a bigger difference in the diffusion at the outlet than the presence of the rosette actually does. And our rectangular tet mesh is the least diffusive of our meshes, but is still not ideal with our tets and nonconformal surfaces. Furthermore, the pressure drop from the inlet to the outlet is about 10 pascals with or without the rosette. And further processing the data is suggested to be performed in order to compare the relative pressure drops with the mixing effects of the rosette to determine if the rosette presents a cost-effective micromixing solution or not. In conclusion, these results appear to indicate that the rosette does not aid in mixing, and however, further development and improvement of the mesh and model need to be performed in order to validate these conclusions. Lastly, I want to end with some acknowledgments. Thank you to Caleb Schabel from Liberty University for his help in the initial modeling of the rosette geometry, and thank you also to Liberty University for providing the computational and financial resources required for this investigation. Here are my references. Thank you for listening to my presentation. Have a wonderful day.